I want to welcome everyone to All About CO2. That's carbon dioxide, domestic water heaters. Before we start this session, we just have to say a huge thanks to our platinum level sponsor, Mitsubishi, who supports all of the work that we do here. You know, at the end of the day, Mitsubishi has the future of heating and cooling technology, all the way down to existing homes who need to swap out maybe a gas furnace or get an air conditioning. They can use dual fuel technology, which we will talk about in the later session and have talked about, all the way to going all electric. That's what I've done with my cold weather climate air source heat pump system, all the way up to massive variable refrigerant systems for large scale multifamily and commercial buildings that can simultaneously heat and cool and ventilate the space. They're going to help you decarbonize, electrify, and they've got some new products coming to the US market, especially that we're going to be talking about today. So we're super excited about that and appreciate all of their support. So with that, again, I want to welcome everyone to All About CO2 Domestic Water Heaters. This session is brought to you by the GreenHome Institute. The GreenHome Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. We're a small but mighty team of 3. Today, I will be your moderator. My name is Brett Little, and I am the education manager here. This course is approved for multiple continuing education units, including, and I got a few too many logos here, our certified GreenHome professional designation in energy and in health, as well as AIA, health, welfare, and safety, which may make it applicable to your state-based design or contractor license. And you can check out the FIAS code sent to you at the end for your Passive House certificate. So with that, I am excited to hand it off to our speakers here, Mike Song and Matt Rash. Mike, Matt, thank you for joining us. Please take it away.
All right. So, yeah, thank you very much for having us. I'm Mike Song with Mitsubishi Electric Trane. I'm the Commercial Regional Sales Manager for the state of Michigan. And Matt, I don't know if you just want to introduce yourself before I get going.
Yeah, sure. Matt Rash, I'm the mechanical application engineer for our central business unit. So I'm kind of higher tier support for project specific application needs, to our sales staff and our distribution partners, and ultimately the engineering community as well.
All right. Thanks, Matt. I'm going to jump right into it. So as everyone knows, we have some changes coming to the HVAC industry, from the HFC phase down, transitioning to lower GW products, and decarbonization electrification goals. While these are all good changes, we want to ensure that we go about this sustainably and not just slapping a bunch of electric strip heat. And that's where we have different products to help meet your needs. Now, while this chart is a little outdated now, many of the states have an electrification push and carbon neutrality goals, and heat pumps are a great way to help achieve these goals, if it is going to be heating with the RF products or on the domestic hot water side. And really, why is there a need for sustainable domestic hot water? In the United States alone, water heater energy use is responsible for emitting over 100 million tons of carbon into the atmosphere every year. And the Advanced Water Heating Initiative estimates that more than 25 million water heating systems in the United States will need to be replaced in the next 5 years. So this is really a large piece of the pie that we can target for decarbonization and electrification goals. So several years ago, the IPCC, which is the Intergovernmental Panel on Climate Change, which is a United Nations body, released a study outlining the plan to get carbon neutrality and net zero emissions, and that's really how the world can achieve these goals. Buildings represent the second largest sector, and the only way to achieve these goals is through the broad adoption of advanced heat pumps. This can be through VRF, mini splits, heat pump boilers, or in our case today, domestic hot water heat pumps. Inside of the building sector, we've done a pretty good job electrifying the majority of the items. However, there's 3 main segments still left to be looked at: space heating, water heating, and cooking. 2 of these 3 can be solved by heat pumps, which would be the space heatings and the water heating. And just to take us all back here for a moment, as I'm not sure how many of you are familiar with what a heat pump is, but for those of you that are not familiar with a heat pump, it's a system that transfers heat from one place to another via refrigerant. The example shown here is a mini split. In the winter, the unit absorbs heat from the outside air and rejects cold air into the environment while supplying hot air to the space. In the summer, it reverses, where it supplies cold air to the space and rejects hot air to the environment. And it really consists of several components. You have an outdoor unit, an indoor unit, and then you have refrigerant lines. And this is an example of a heat pump, but be VRF or mini splits. That would be heating and cooling your home. The domestic hot water heat pump we're going to get into today, similar concept, but different in execution. And to produce the heat in the winter, heat pumps have to absorb heat from the outside air. As the air gets colder, there is less heat to be absorbed. This is what we call D rates, and it's important to size your system with the proper ambient temperatures. And technology really has came a long way from what some of you may be used to in terms of the D rates. So no longer do you have to be concerned with severe D rates on products like VRF and mini splits. And this chart is an example of a VRF system that you can see at negative 22, it still provides 70% heating capacity. Now the second chart here is for a domestic hot water heater, which has harder D rates than VRF, but still operates all the way down to negative 35. We just don't have data down there. And you really don't need to be too concerned with the D rates as long as you work with your manufacturer to properly size the project for the correct ambient temperatures to ensure you always have your hot water. So now we're going to jump into the actual domestic hot water product. And what does a domestic hot water heat pump look like? So it can produce 176 degree water all the way down to negative 35 because of the CO2 refrigerant. It's going to have COPs from 3.88 to 4.52, utilizes the natural refrigerant of CO2, and they can operate down to negative 35. And depending on the manufacturer, some will operate down to negative 4 and require backup electric heat for colder climates. So why do we use CO2 refrigerant? It's a great natural refrigerant that performs very well in high flow, low flow, high delta T situation, which is what we have here with the domestic hot water heater. It's got a GWP of 1, an ozone depletion of 0. It's non-flammable, non-toxic, high pressure temperature refrigerant, excellent low ambient heating performance, and highly efficient. So how do we produce these 176 degree water temperatures? It's really all because of the CO2 refrigerant. And the CO2 refrigerant is considerably higher pressure than R134A, but it's fully contained in an outdoor unit, which is fully outside of your building. And as you can see here, when you compare CO2 to R134A, it's at a higher pressure. When CO2 is rejecting heat to the water, we're in the transcritical cycle, and the CO2 is in the supercritical fluid state, which allows us to produce hot water all the way down to negative 35. Also, these type of products are going to have a lower carbon footprint. So heat pump water heaters can offer a 78% reduction in carbon footprint when compared to a 98% condensing boiler, and a 66% reduction in carbon footprint when compared to a district electric heat. So it is really a great option, these products, for domestic hot water heat and decarbonization electrification. Additionally, because of the COP, which is a coefficient of performance, which is basically how much energy you put into a system, how much energy you're going to get out of it, we have 3.5 to 4.5 times more energy as heat than electricity consumed. This will allow owners energy savings up to 60-70% compared to electric resistant water heaters. So it's definitely a much better option compared to those type of systems. And in some markets, there's even going to be incentives to move towards these type of products. And we've seen them across the country. Different markets are moving that way already. And just one additional thing in terms of maintenance. So these aren't going to be like maintenance heavy products like, you know, other systems can be. It's really going to have a strainer installed near the unit to keep foreign materials. So you have to clean that and make sure it's good. And then you're going to have proper tank maintenance like you would with any other product. You're going to have to clean the products and periodically ensure internal parts are free from scaling and debris, and then check and clean the evaporator coil as necessary. So now I'm really going to turn this over to Matt Rash, and he's going to take you into the components of these. So Matt, I will stop sharing, and you should be good to go.
Okay, thank you, Mike. So can everybody see my screen okay?
Yep.
At least, okay, great. All right, so we're going to get into more of the details and specifics of the componentry, application, sizing considerations. So first off, we'll start kind of 10,000 foot level, looking at major components of these systems. So this is just a typical schematic, pretty representative of heat pump CO2 based domestic hot water heating systems. Now, this may vary slightly from manufacturer, but I think you'll find this fairly common in terms of application. This is obviously based on the Mitsubishi QHV product, being an air source outdoor located CO2 heat pump water heater. But even though this heat pump has basically a double wall heat exchanger, and typically they do, in the event of failure or corrosion of one of the sides of that heat transfer, whether it's the refrigerant side or water side, there's still concerns with regard to water quality and contamination. And because you're dealing with such high pressure refrigerants and wanting to minimize service work that may be required through the life of the building on that outdoor unit, most manufacturers, including Mitsubishi, are choosing to separate the potable side of the system from the actual heat transfer that's occurring directly through that outdoor heat exchanger. And so that's typically done with a brazed plate heat exchanger that's potable rated, located indoors. So between the outdoor unit and this indoor heat exchanger, we're going to have a closed hydronic loop. And this loop would have all the typical accessories and components that any conventional closed loop system would contain: air separators, expansion tanks, pressure reliefs, flush fill valves, things of that nature. And we'll show some of those details further on in the presentation. And then indoors, where that heat exchanger is located, there would be an additional variable speed hydronic pump that is required to circulate cold water from the storage tanks through that heat exchanger to pick up the heat that heat pump produces and then send it out to that storage tank farm. Now, with heat pump water heaters, typically because of economy of scale and upfront cost, and the fact that they're optimized for really running at full peak capacity and then shutting off and wanting to minimize the number of cycles per day that occurs, it's not good for the longevity of the equipment. You're dealing with typically very low charge rates, or in other words, lower generation rates and much higher storage volumes than what you're conventionally used to seeing in typical domestic hot water systems. So because of these low charge rates, when I mean charge rates, hot water supply rates to these storage tank farms, and disruption that cold inlet water can cause to that total tank volume, temperature distribution, typically most manufacturers, including Mitsubishi, are only endorsing series tank arrangements, which is what you see here. So it could be a single tank system, but typically it's more than one tank. You're feeding hot water in first to what's called a hot tank upstream, and then out of the bottom of the hot tank and into your final cold tank, and then introducing cold water in that location. And pulling from that bottom side of the cold tank, obviously to maximize efficiency and heat output of the heat pump water heater. And so this heat pump water heater, like I mentioned, is meant to really go operate almost at full demand capacity when it sees those tanks depleted, recharge the tanks, and then shut off. And so this equipment really is not designed and optimized for long, steady state periods of low delta T. That would be more indicative of a heat pump boiler for conventional heating hot water. And there are products like that you'll see coming into the marketplace in the near future. This is not that product. It's meant to recharge tanks and then shut off, basically. So it's not meant to handle long, steady state loads. And those would be loads representative of building heating hot water recirculation loads that any commercial domestic hot water system would have. And so instead of putting those loads onto this primary heat pump system, those would typically be handled by something called a swing tank. So we would feed the hot water supply from this tank farm, if you will, that's been generated by the heat pump, and then into a swing tank. And that would have an electric resistance element that would provide that temperature maintenance during long idle periods. And so just like with any conventional domestic hot water system, you'd have a temperature mixing valve in that building and a heating hot water recirculation pump that would bring back hot water from the farthest fixtures to make sure you always have hot water primed out into the building. And again, the main goal here is to keep that off of the CO2 heat pumps and allow those to be utilized for what they've been designed optimally to be most efficient for, which is to recharging these primary storage. This in a little bit more detail as we go here. go through this. So you could really start breaking these systems up into three: primary side, which is your outdoor heat pump water heater with associated controls, all those closed loop components, that plate and frame heat exchanger, not plate and frame, but brazed plate heat exchanger indoors. And then what's called, again, as I mentioned before, the secondary side that has some additional controls, that variable speed pump, your primary storage tank farm, and then your recirculation and swing tank componentry. And so what you'll find with most manufacturers, including Mitsubishi, is they want to be directly in control or involved and in control of these primary side and secondary side and storage components, because those are all paramount to proper operation of the system and achieving and maintaining the domestic hot water demand that's required for the building. The recirculation and swing tank side, again, that's fairly common on the recirc side for most building designs. Many manufacturers will offer options for swing tanks. We do as well, but those aren't required to be typically procured from the manufacturer. So with these systems, again, because they're series tank arrangements and because of very low recharge flow rates and wanting to maximize stratification in the tanks and temperature sensing requirements for triggering on these heat pumps, these are typically not off-the-shelf tanks. Again, this may vary by manufacturer. These are usually custom engineered tanks that aren't available through normal supply channels. And so manufacturers typically will partner with specific tank manufacturers to construct these tanks specifically for their offering. So these are some common sizes that you'll see available. This is more indicative of Mitsubishi's offering. Tank sizes, starting at 175 gallons up to 500 gallons. And then we're also looking at tank sizes up to 1,000 gallons as well. But these tanks are specifically designed for these series applications. They contain sparge fittings to minimize velocity and velocity jets inside of those tanks that really promote mixing, which is not advantageous. We want to maintain stratification in the tanks. Again, they're going to have multiple thermistor locations. Again, that ties into the control side of these heat pumps in terms of triggering the heat pumps on and off. You may see these with glass lined or duplex stainless requirements. That's usually comes into play when you're dealing with hotter storage water temperatures well above 150. So again, this just kind of graphically depicts what these sparge fittings are that I mentioned that are important to be incorporated into these tank designs. This is more of a generic depiction of this, but it represents kind of the goal and the strategy you're trying to achieve with these fittings. And again, that is to minimize mixing inside of these tanks and maintain a nice a thermocline through the tanks. We want to see that stratification. We want to maintain hot water up near the top of the tanks and keep the cold water contained to the bottom of the tanks to that heat pump water return or that separation heat exchanger. And again, this is done by minimizing the effects of a normal velocity jet that would be present under a high drawdown event. So these are designed basically these cylindrical tubes with multiple perforations, usually to keep the velocity below, I think, 4 feet per second is a typical goal. And again, the goal is to minimize a jet situation, velocity jet into that tank that's creating turbulence and mixing and maintain that thermocline. Again, I mentioned the separation heat exchanger between the outdoor heat pump primary loop and then the secondary potable loop. And this may vary by manufacturer. This is just an example of what Mitsubishi's partnered with through SWEP. So it's a brazed plate design. It's important that these are sized correctly, and you have to pay fairly close attention to this because, again, you're dealing with very low charge rates on the primary side with a high degree of water flow turn down depending on loading. So near the end of tank charge, you could see your higher flow rates near the maximum. And then under extreme cold ambient conditions, you could see flow rates that are possibly 1/10 of those maximum flows that can be experienced. So you have to be careful with brazed plate heat exchanger selection. You have to look at multiple sizing criteria. It's important to make sure that you have a specific fluid film shear stress in between the plates for the majority of the operating hours to avoid corrosion because of that potable side and mineral deposits that could occur if you don't maintain sufficient velocities through this. So usually manufacturers are selecting these specifically and pairing them and offering them as part of the package. So it's important to comply with that and typically not source them from third parties. Again, swing tank sizes are typically available in different increments from manufacturers. This is just an example of some of the ones that Mitsubishi offers, up to 300 gallons. You can see here with different voltages available. Again, this is going to vary by manufacturer. This isn't, as I mentioned, something that you specifically have to buy from the manufacturer. We're more concerned typically with that primary side and secondary side with the storage tank farms. Again, I kind of already alluded to this before, but that secondary side turn down is important with these systems. That ties into that, that critical heat exchanger, brazed plate heat exchanger selection. And I talked about the high degree of turn down, and that's not uncommon with this equipment. So again, near the end of that tank charge cycle where you've almost recharged that tank up, with our equipment, for instance, you could see flow rates near 8 GPM right before the unit shut off. And then at really cold ambient conditions where the equipment's derated, in order to maintain those discharge water temps, to maintain that thermocline and that storage temperature that you're trying to achieve on the tanks, you could see water flow rates down to 0.8 GPM or even possibly lower when you get down to that minus 35 level that Mike mentioned. So you're dealing with turn down ranges in the range of 10 to 1, if not higher at times. So it's paramount to have proper controls in place, proper pumps that can actually handle that degree of turn down. This is really almost like process level water flow modulation requirements. So, if you start looking at this with typical pumps, I shouldn't say typical pumps, but common potable DC direct commutated pumps, you can see some challenges. So if this is just an example of a Magna 3 pump, which is a potable rated pump, where if we were selecting this for say 8 GPM at its maximum speed curve, and then having to balance this with just a single balance point to achieve this ultra low flow turn down at its lowest minimum speed, you potentially run into issues, all right, when you're near the end of that tank charge cycle and not being able to get up to that maximum flow rate, that in this case a maximum flow rate of around 8 GPM, because you're dealing with two system restriction curves on your pump. So oftentimes with more advanced solutions, not only is the pump a variable speed pump, but you may have two different balance positions with, say, a three-way diverting valve with different balance positions that have to be set in the field, and then controls integrated with that, so that when you need to get to those lower flow turn downs under those cold ambient conditions, you can achieve that with basically two balanced system restriction curves. So you're toggling back and forth at those cold ambient conditions to hit those specific low flow turn downs that are required. So those are things that have to be thought about as part of the application. And again, this is why it's important to make sure the manufacturer's involved and their controls and their solutions are being applied with the product so that it can achieve those discharge water temps at all times. This is just kind of representative of something, the phenomenon you can see in these systems if you don't have proper flow turn down. So this is obviously looking at our equipment, where if you had a situation where you were limited to 1.5 GPMs instead of 0.8 GPM or lower, and if you were targeting 150 degree water temp, these solid lines represent your water flow rates, right? And then your bottom axis is your ambient conditions. So these are just different water flow rate requirements at different entering water temperatures into that heat pump water heater. And so as ambient temperatures drop, your water flow rates must drop in order to maintain that 150 degree water set temp target in this example. And so that's what these dashed lines are indicating. And you can see here where if you are limited with flow turn down to that 1.5 GPM level, Once you start getting below, 0 degrees, -4 roughly, you start to lose control of discharge water temperature going to your tank. And these solutions really need to be considered with the manufacturer. Not put this on the designer or the installer to accomplish all of this, because it takes a pretty significant degree of forethought to make this all work together correctly and effectively. So there are ways to simplify this, and you'll see that this is becoming more common, I think, with some of the major manufacturers in the domestic water heat pump world. You start looking at all these components that are required. Again, where it really gets complicated is on this primary to secondary side and all the controls and piping specialties that go with this. And we'll get into some of that in more detail here in a minute. This is just kind of an isometric depiction of what's required here at that brazed plate heat exchanger between the heat pump water heater and the secondary side. So you've got buffer tanks, expansion tanks, air separators, pressure relief, temperature sensors, pumps, controls. So that's a lot of field work that's involved. And that can be a challenge for a lot of the Division 23 or Division 22 type contractors in the plumbing realm. This is kind of outside of the wheelhouse in a lot of cases. It's definitely more suited to Division 23 on the mechanical side, but still, it just opens up the potential for more issues, more potential rework in the field. So manufacturers are exploring and going to skid options. Mitsubishi's doing this. Other manufacturers have as well, to really encapsulate this entire scope on that primary secondary side into a single skid package with self-contained controls. So again, this simplifies the application. It also opens up some capabilities for greater staging, N+1 lead lag rotation type strategies, depending on the controls that this is paired with. So again, that's just kind of high level looking at major components. I'm going to touch briefly on performance data, modes, and energy analysis, and then we'll come back and start looking more specifically at sizing considerations and more detailed application information, again, on those piping diagrams. Just wanted to check time here real quick. All right, so CO2 heat pump capacity, derates, operational modes. So systems in colder climates, typically, and this is pretty obvious, I think, are going to have to be critically sized, for those low ambient conditions. So that's what we're fighting. Just like with any heat pump, as we move into more northern climates, we're sizing critically for these derated capacities. So oftentimes manufacturers may offer multiple modes, and you'll see that published. Mitsubishi offers this as well with our heat pumps, and these offer different peak output capacities, and they'll be labeled, or they may be described as maximum capacity versus energy save type modes. But really, these are just trade-offs under higher ambient conditions to achieve higher recovery rates at the expense of higher peak kW inputs. So they're really more suited, when you see different mode options like this, they're more suited for time of day rates, off-peak demand tier rates, again, where you can utilize this faster recovery, or be part of a demand limiting strategy, load shift strategy, where you may have load up periods where you store hotter water temperature in the summer, and then demand limited periods where you're load shedding. And so, regardless of this, and again, this is representative of Mitsubishi's gear, the QHV, what you'll see is, regardless of the mode that these are in, you'll see that the COPs are fairly similar across all these modes. So for Mitsubishi, for instance, we have 3 different modes: a max capacity, an energy save 1, energy save 2. And I'll show some of the differences of those in a minute. But you'll see between -13, where we chart down to upwards of over 100 degrees, you'll see you start out with a COP just slightly over 1, and then upwards of 4.5 at these higher ambient conditions. So there is some differences in shape here with COPs, but it's, if you trend these lines, it's fairly consistent, across these different operating modes. So again, these aren't really, the term energy save is a little misleading. They're not really saving energy consumption significantly. What they're giving you flexibility in doing is achieving higher recovery rates under warmer ambient conditions, but you have higher PKWs that correspond with that. And so you'll see charts in manufacturers' data, and obviously this is based on Mitsubishi again, that represent peak capacity output versus power input. And that's what we're looking at here. So you have these three different modes in the case of Mitsubishi. These top set of curves are your capacity output. And I apologize, this is all in KW because this is how the factories in Japan chart everything in KW. But your top set of curves are maximum capacity. And your lower set of curves are power input. And so you can see with winter operation, really all of these curves, regardless of the mode, is where you're typically critically sized for, especially in northern climates. All of these curves in terms of capacity and power input pretty much converge, down below this roughly 32-degree mark. You can see the curve shapes all kind of line up there. It's really during these summer conditions, again, where you have this trade-off of higher peak output capacity, depending on the mode, with a corresponding, demand input penalty associated with that. And so again, if you have time of day rates where that's advantageous, if your building profile is such that you could take advantage of those higher recovery rates during the summer months, and that makes sense, you have options to do that, or to curtail those peak demands until off-peak hours, and do load up strategies to store hotter water temperatures in the morning, if that's something that makes sense based on your specific utility rate structure, and then demand limit during those peak hours in the afternoon, which is probably more common with most utilities. So there's higher level controls typically that obviously have to be involved to accomplish this. So you'll find with these systems, they're going to have supervisory panels in many cases. That's the case with Mitsubishi, that have backnet capability to tie into building management systems to be part of that integrated demand response strategy. So again, more commonly, this would be something like a time of day off-peak period, where you have advantageous demand rates, and you need to demand limit during a peak period. So you may preload, you may have load up periods that the BMS system communicates to these heat pump supervisory panels, and you'll pre-charge your tanks maybe to hotter water temperatures than what you could achieve during those critical heating dominant periods, or colder ambient periods, I should say, in the winter months, where you have that higher heat output available, and pre-charge those tanks to higher temperatures to get you through those peak demand periods, say in the afternoon during the summer, if that made sense based on your specific utility structure. So again, you'll see with these supervisory panels, they're typically a web-based GUI interface, remote status and error reporting, typically offer scalability to multiple heat pumps, skid package combinations, and gives you scalability across multiple buildings in terms of a single interface point. In terms of assessing energy performance with these systems, you really have to start looking at manufacturer correction data, capacity data, and power input data. And we kind of just illustrated that information previously, again, on those slides when we looked at those three different operational modes. And then from that data, you can ascertain, effective COP or EIR, energy input ratio. And then you really need to apply that to get an accurate assessment of savings to an average representative profile. And when I say profile, I mean a domestic hot water load profile. And then that has to be applied also with correct ambient conditions. So you really need to pull in TMY data, typical meteorological year data, especially if you want to look at time of day type analysis, as opposed to just bin analysis, unless you can break the bin, if you have tools to break the bin data up into specific times of day. So this can get fairly complicated, and there's not a plethora of tools out there that can accommodate this especially with regard to specific manufacturers. So you want to look to manufacturer tool sets if they're available. Mitsubishi makes some Excel-based tools, and anybody's welcome to that tool. And it'll allow you to put in climate location. It also includes EIA emission rates for multiple states. You can look at CO2 emission impacts. You can enter conventional system inputs, your CO2 heat pump water heater design. Obviously, this is based on Mitsubishi's gear. And then you can enter an ASHRAE average profile in the absence of knowing a specific hourly profile. And that's really key. And that's part of the challenge in assessing this. Designers especially on the plumbing side, are used to dealing with kind of empirical rule sets and peak load heat pump water, or I should say domestic water heating plant designs. But when you start looking at analysis, again, you really have to look at average representative conditions, and that can be hard to obtain, or a lot of designers just don't have a good feel for what that is. So luckily, ASHRAE publishes data on this, both for peak design purposes, I should say peak design day, as well as average conditions. And so you really want to start referencing those average profile maps, and they offer this for multiple different vertical markets, elementary schools, higher education dorms, office buildings, things of that nature. And so this this tool I mentioned will allow you to pick from those different profiles that it uses as part of that analysis. So that's something to be mindful of when considering energy savings. And so very quickly, you can get reports like this, where you compare the different systems, look at average seasonal COP, demand, consumption savings, CO2 impact. So again, look to specific manufacturer tool sets. Again, Mitsubishi has something available, and we can certainly share that with anybody that's interested. Okay, selection process and applications, getting into a little bit more of the details. So this is probably where one of the bigger challenges come into play, is how do we properly size these heat pump water heaters? Because as I mentioned, these are optimally designed to come on, operate almost at full capacity, and then shut off once you achieve that tank charge condition, once you've replenished those storage tanks. So really, they only start modulating near the tail end of that tank charge process or cycle. And again, because of economies of scale and the cost of this, what you're seeing is storage volumes that are 1.5, 2 times or larger conventional domestic hot water heating sizing methods, with very or much more reduced generation rates from the heat pump water heaters. And again, it's a twofold consideration, both upfront cost and the fact that these units typically aren't optimized for long steady state periods of operation at low delta T. Again, they're meant to come on, operate at almost full capacity, and shut off. So we don't want those cycling excessively throughout the day because they've been drastically oversized. So it's more analogous to load leveling an ice storage chiller. And so your hot water storage tanks are basically your ice storage tanks, and your chiller's been replaced by these heat pump water heaters. So in that scenario, that analogy, you've got an ice storage chiller, you're load leveling it. Your goal is to never run out of ice. Some hours you're burning ice, some hours you're storing ice, but you're keeping that chiller loaded through the majority of the hours. And that's kind of the goal with these systems. We like to see these heat pump water heating systems designed on a peak design day to have at least 10 hours of runtime, because again, under average conditions, they'll see less than that, and we don't want to get into excess cycling. And there can be lockouts if those number of cycles are exceeded. And so again, when you start looking at typical kind of empirical based methods by ASPE or ASHRAE, where you're adding up fixture values, gallons of water per hour per fixture, and then applying things like a demand and a storage factor to these. This is just one example of those methods out of ASHRAE. Those are difficult to extrapolate to these alternate designs. Again, applying this mindset where you're going to have higher storage volumes and smaller generation outputs, recovery rates, I should say, from these heat pump water heaters, and you're trying to maximize hours of runtime. So really what we need is we need an hourly profile. Just like we do with energy analysis, we need an hourly profile to analyze this under those peak design scenarios. And there's different ways to look at that, based on your known maximum peak gallon per hour rates that you have for the building, but that really needs to be extrapolated to an hourly profile. And typically you want to apply that to, more than one 24-hour cycle, because depending on how that profile looks, you can have carryover effects. If you've got 2 design day scenarios back to back, that can have impacts. So again, going back to some sources like ASHRAE, those are good resources when the designers don't have that information. And that's, again, a common thing we'll find and see is designers just don't have a good idea of what that hourly profile looks like. They're not used to sizing water heaters that way. So again, they know what the peaks are, and they can take that data and apply it to these ASHRAE profiles. Again, instead of using the average data that ASHRAE publishes, we would be looking at one of these design conditions. So they have a couple. They've got a days in which the maximum hourly use occurs, and then days in which the maximum daily use occurs. And so again, these are dynamic effects because they impact how quickly storage is depleted and how long those water heaters run. And then you can extrapolate those peaks using these profiles. And then, there's other sources you can use to get a good gut check in terms of where you're at. ASHRAE, again, if you look in, I think it's their application sections, they publish some charts like this that are very conservative because they predate modern low flow fixtures, but they'll give you data like maximum hourly and maximum daily, gallon per student in the case of a dorm, or a gallon per person in the case of an office building. It just depends on the building type. So looking at those 2 sources along with the designer's peak gallon per hour rates, you can typically arrive at a profile. And so you can start applying these profiles, looking at heat pump output capacity that you have available, and potential storage volume that you think you could fit into the occupied space, and you can start to analyze this. And you could do this in a manual method, or with an Excel-based type tool manually. And again, the goal is to look at this at least over a course of 24 hours, preferably over more than one 24-hour period because of that carryover effect, and analyze this basically total net system capacitance, if you will. And so you can convert these gallon per hour draw load rates into an equivalent BTU. You can convert the storage volume that you store at that water temperature into an equivalent BTU. And again, you're looking at this in terms of, capacitance. So these loads by hour, what your starting capacitance or storage volume is, and what you have available from the heat pump water heater. And you can analyze these effects over the course of, again, typically a couple 24-hour periods, and determine, hey, am I running dangerously close to depleting my storage under any given hour? And B, do I have enough runtime? Is my heat pump sized, in sizing optimized with this storage combination to make sure that it's running enough hours out of the day? This is an example from an actual men's dormitory. I think this was like 450 people with 1,500 gallons. And I think this was an example where it was extrapolated to a max hourly condition per ASHRAE. And so you can see what this profile looked like when this was mapped out over the course of 24 hours. So in this scenario, we were pairing, I think, over where you can see here in the graphs, over 600,000 BTUs, 600 MBH worth of CO2 heat pump water heaters, along with 1,500 gallons of storage. And we had plenty of storage reserve. Storage is indicated by the blue. At no time did this ever get depleted. And you can see by the red output, that's your heat pump output. We've got, close, in this case, I think it was close to 14 to 15 hours a day, equivalent hours. Some of these are part load hours where that heat pump is running. So that would, completely be valid in this scenario. We've got a heat pump that's running more than 10 hours a day. We've never depleted our storage. And again, you can play with this and iterate it iterate it through, multiple iterations, trading off, heat pump quantity, heat pump output versus storage. And so this is kind of a tedious, labor-intensive task to go through this. Again, there's ways to automate this in Excel-based tools, which you could do. And we have some of those that we've done in the past with certain projects. But to simplify things, there's other tools available in the marketplace that are much more robust, instead of having to do this manually, where you can apply these profiles and achieve basically a sizing curve that gives you this trade-off between heat pump output and storage volume requirements. And this is a tool developed by Ecotope. This is a third party. They don't really have any direct affiliation with any manufacturer. So they do consulting work primarily in the domestic commercial hot water heat pump realm, especially with multifamily projects. They've utilized multiple manufacturers' pieces of equipment. So they'll do turnkey type engineering consulting services to design and implement these systems. And with that, they've done quite a bit of metering, post-install metering on buildings, and gathered quite a bit of empirical data from that. And they built that into their tool as well as alternate methods from these kind of ASHRAE standardized methods, more specific to multifamily. But they've also added capability to do custom profile inputs, again, based on these ASHRAE profiles that you can pull from. And so, again, this really kind of simplifies it, and it's much more robust. I think they do this in 1 minute increments. So it's not just an hourly analysis. They're doing it in 1 minute increments over the course of, I think, a couple 24-hour periods. And so this is a link to this tool. Again, we'll provide this in the presentation that everybody gets a copy of. And anybody can go to this site and start playing around with this and putting in inputs, based on building type or custom profiles, and generate. Again, the end goal is to generate a sizing curve like this that you see here. I know this is a little bit hard to see, but again, you've got a trade-off here, and they actually allow you to slide a scale where you can trade off storage volumes with heat pump output capacity. And again, once you get this information, once you've gone through this process, looking at your profile and achieving the sizing curve, you can take that data back and start looking at the manufacturer correction data, for what can be achieved from those heat pumps, and see what makes sense in terms of, number of CO2 heat pump water heaters that you need to apply. So Mitsubishi has a software like this. It's called Diamond System Builder. This is also available to the public. You could go to our site and obtain that. And once you have that information in terms of storage volume, what you're going to store at, temperature, and the minimum output capacity you need, again, from this sizing type curve, you can bring that data back, and this software will provide the recommended number of heat pumps and storage tanks, at least based on our offerings, that would meet that load requirement. So that's kind of the process that you have to go through and think about. Again, the big takeaway here is that applying typical empirical methods, are a challenge, and oftentimes are, again, from ensuring you have sufficient number of operating hours and minimizing upfront cost. Those conventional type methods usually aren't suitable, and so you really want to be going through this process. Okay, jumping into some of the more finer details of the application and the specialties I mentioned before. I'm going to look at this with a little bit more granularity. When we start looking at, again, these piping requirements and specialty requirements between the outdoor unit and indoor. Outdoors, you're dealing with basically 2 pipes, supply and return. Typically, these are going to have to be heat traced. Although there may be allowances for glycol, that's something Mitsubishi's looking at allowing at least up to 30% propylene. But again, depending on climate, it's probably a good practice to incorporate both glycol and heat trace, depending on what concentration you can get into that loop, especially for burst protection. So again, 2 pipe sizes, 2 pipes from the outdoor unit to your indoor location, heat traced, typically with glycol. You're also going to have, because these are heat pumps, you'll have condensate pans at the outdoor unit. Those pans will have to be heat traced. You may have a drain line from that connection not may, typically will, that has to be heat traced as well to the point of termination. The units need to be elevated above the snowfall height, snow drift height. We'll talk about some of that in a minute. So coming indoors, again, we're going to have that primary secondary heat exchanger. You'll need a means of pressure relief, an air separator, gauges, temperature and pressure gauges, a buffer and expansion tank. These could be a combined tank. Typically, they're broken apart into two separate items. You'll also have to include a fairly robust strainer, typically 60 mesh, to protect these heat exchangers in the water source module. And then you're going to have flush and fill valves. You'll also have flow sensing requirements, typically with a fairly high degree of precision in order to activate and cycle on typically a direct commutated variable speed pump on that secondary side. So I kind of talked about that before. Because of the high degree of flow turn down and modulation, you're dealing with direct commutated pumps in most cases, potable rated. You have to have a control means of triggering that. You have to have temperature controls in this in order to maintain and hit that discharge water temp target. So again, this is your primary side between the heat pump, a secondary heat exchanger, and then this would be your cold water supply down here at the bottom coming from your storage tanks, that cold tank that I mentioned before, and then hot water supply being generated going to that hot tank. So again, taking this further, when we start looking at the tank installation, again, you've got that hot water supply from the secondary side of the heat exchanger that's coming into that hot tank. You'll see a sparge fitting in those tanks up high at the hot connection. You also see a sparge fitting down low at the bottom connection. So you'll bring the hot water into the hot tank, out of the bottom of the hot tank, and then into any subsequent tanks. Again, the last one being the cold tank. And then we'll be drawing cold water typically out of the side of that cold tank down low back to the heat pump separation heat exchanger. This says from heat pumps, but this really should be to that separation heat exchanger. And then the cold water would come in typically through a separate connection at the bottommost position of that cold tank through that sparge fitting. And again, this is probably one of the most critical considerations here, is we want that cold water introduced through that sparge fitting down low to maintain stratification, to eliminate a velocity jet in that tank that's going to promote mixing. And again, size that sparge fitting correctly so that you have low velocity exiting, that cylindrical sparge fitting through those perforations. Again, to gradually and slowly introduce that cold water at low velocity through that tank and minimize disruption. So again, series tanks is what's typically being promoted in these applications. And then again, on the mixing tank side, let me back up here. The hot water supply from this hot tank, again, you've got hot water coming from the heat pumps, but you've also got hot water leaving this tank, going to, not directly to the mixing valve, your main mixing valve for your building domestic hot water, but first going again from the storage to that swing tank. So again, the swing tank's going to handle that steady state idle load, that maintenance load for that building heating hot water recirc loop. So you're going to have that pump that would be by others. And again, this is pretty common and typical on this side, the recirc side with mixing valve for most domestic hot water systems. So you'll have your recirc water coming back from that pump. You'll have balance valves to redirect a portion of that through the swing tank, and then a portion back with cold city water into your electronic mixing valve typically. So you may be storing at 140 to 150 or hotter, and you're delivering to the building typically at 120. So it's important to store, obviously for bacterial, microbial growth, protection against Legionella. We're storing in our primary storage tanks and in the swing tank, maintaining temperatures typically at 140 or above. All right, so scalability. So, as I mentioned, and this is the case with, I think, a lot of manufacturers, although some offer bigger combinations than others, but depending on the size and the controls that are implemented, typically you have the capability for scalability with multiple heat pumps. You're typically not relying on just a single heat pump for, larger jobs. Now with smaller projects, you may just have one or two, but typically you're dealing with multiple heat pumps. And again, depending on how those are implemented with controls, and that's important, you want to look at that with the manufacturer. You're going to have scalability options. And with that brings potential redundancy, minimizing disruption if you do lose a specific heat pump. So again, with larger projects, this becomes more important. And so with our system, obviously this may look different depending on the manufacturer. That scalability exists. So we only have a single size heat pump water heater, but again, it's scalable. And for each heat pump water heater, you're going to have to repeat that scope of work for that primary to secondary heat exchange. So again, the heat exchanger, all that closed loop accessory components, the controls, and that secondary side pump with all the temperature controls, you're just repeating that. So you've got dedicated water connections to each of those heat exchangers, and then reverse return piping basically between your storage tank farm and each of those secondary heat exchangers. So again, with the skid solution, this simplifies things drastically, and really takes the thought and the process of all that field work kind of out of the equation for the installer, and really eases the burden for that installation team. So looking at a skid type installation, and this is kind of indicative of one of the projects we've looked at recently. This is actually a large dormitory with 11 skid packages in this case. So those are kind of indicated by these gray boundaries here in these boxes. So again, that would each of those skid packages would contain all this componentry that you see here on the screen between the primary and secondary side with the controls. And so you would have dedicated water lines, supply and return, from each of those heat pump water heaters. And then on the storage side, you would basically reverse return, just like this illustrates in this drawing. You would reverse return each of those skid packages accordingly. So fairly compact footprint. And again, the biggest benefit here, even though this is obviously a lot of pipes to deal with on the primary side to each of the heat pumps, in this scenario, if you lost a specific heat pump, you've taken out less than 10% in this case of your total capacity. So again, we're sizing these systems for these peak design day worst case scenarios, but in reality, for most operating hours, they're going to be below that. So your ability to maintain and continue operation in the building is really enhanced by taking on strategies like this under larger installations. All right, so cold climate protection. I know I'm getting a little bit tight on time, so I'm going to speed this up. I think we're getting near the end of this section, but cold climate protection is important. I mentioned this before, but the units need to be elevated above the snowdrift height. You want to have countermeasures to keep wind-driven precipitation, hail off of the coils. I talked about heat trace on the pans and the water lines is important. So just pay attention to that with manufacturer requirements. And so I apologize, Mike, a little bit over here, but I think we're going to hand it back to you, and you're going to talk about a couple case studies here real quick, and then we'll wrap up with some questions.
Yep.
Yeah, Mike, before we hand it off to you, I just want to do a quick reminder for those of you who do need to get going. We're at the hour. You have, as long as you've been here for the entire session and you're appropriately logged in, make sure to take that survey that pops up at the end or that's emailed to you in the next day. Otherwise, you are approved for your Con Ed, so you can get going. You can check your spam at certs@gutenbergcerts.com and you'll receive your certificate there. Again, this is for those of you watching only live, not talking about the recording. And you're good to go if you have to get going. But otherwise, we're going to keep going a little bit longer for Q&A. So I hope you'll stick around and join us for more conversation. So there you go.
Yeah, thank you. And this part's gonna be pretty quick. Only a few more slides left. So we just have a couple case studies of projects that have been installed in the United States. And one question was out there earlier, and I just wanted to mention that while this product is new to the United States, these products have existed across the world with all manufacturers for years. You know, our products have been in Scandinavia for over 7 years, so much colder than Michigan. So you can have some confidence that everything's going to work properly. So this is an example of a project called the Bayview Towers in Seattle, Washington, where we converted 100-unit low-income multifamily housing from a old electric boiler to a new ultra efficient commercial hot water heat pump heating system. They chose to make a little skid package and a housing off site here. That is not what you have to do on all projects, but this is what they chose due to the space constraints they had. So there was just one hot water heat pump with controls package and then a pre-fabricated offsite skid assembly. So it was a very nice, clean solution that they utilized on this project. And the energy use, they went from using 230,000 kilowatt hours to 95,000 kilowatt hours per year. So energy savings are expected to translate to about 15,000 in annual operational costs. And in Seattle, they actually have rebates, so they had a $50,000 rebate as well. So it's a very nice solution for that owner. And a second case study is called the Hotel Marcel in New Haven, Connecticut. So this is a 165-room hotel that was converted, including a restaurant, gallery, and meeting spaces. So this building is a little bit larger, so it utilized 3 CO2 heat pumps, and the result was the first net zero hotel in the United States. So I don't have any numbers yet because this project was just recently completed, but it's a very nice hotel. And if you're ever in Connecticut, and we want to say the first net zero, it's a great location. So really, this is the last slide here. The takeaways. The CO2 heat pump water heaters present an energy efficient solution for sustainable high volume domestic hot water. Optimal performance for these requires collaboration with the manufacturers. These products are different, like Matt mentioned, than the old boilers. So you're gonna have to work with the manufacturers to ensure it's proper. And then updating commercial buildings with CO2 heat pump water heaters can really reduce carbon emissions significantly, and in some instances qualify for sizable rebates. So thank you all. That's all I have, and that's all we have in terms of the presentation. I guess we'll do some questions now.
Yeah, thanks, Mike, and thank you again, Matt. And just again, a quick reminder that this session is being recorded, so it will be available for those to rewatch on our YouTube channel. Share it online, share it with friends or colleagues, catch anything you miss, and get caught up on it in any other way. The other thing I want to remind everybody who's watching this in the future on demand, but not right now, in order for you to get your continuing education units, you need to make sure to take that quiz with an 80% passing rate and then complete that quiz successfully, and you will receive your Con Ed CO2 and all that. And as always, we need to say a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, our nearly 300 members. We're almost there. We hope you'll join us to help us get there. And our top tier sponsors who are helping you decarbonize, go all electric, including Mitsubishi and Rheem. Huge thanks for their support, and all of our sponsors who are helping you meet these goals to succeed. So yeah, there's been a lot of conversation, a lot of questions that have come in, and we do have time for more of those for all of you who want to ask some questions. I think the biggest clarification we just need to get here is we're talking about a system that is just for water heating. I know there are all sorts of systems out there that are heat pumps, whether they be ground source or air source, that can both simultaneously heat water and condition the space. So just to be clear, if it wasn't made clear at the beginning, we're specifically talking about systems that are just heating water. And if that is true, then where are we at with being able to heat space with CO2? What is the challenge and opportunity there?
So Matt, I don't know if you want to really answer this, but CO2 as a refrigerant in general is good for like a low flow, high delta T scenario. So like we have someone's question came up about radiant heat. We have a product coming out that's going to be a boiler replacement that is designed for a high flow, low delta T, but it doesn't utilize CO2 refrigerant. Matt, do you know what refrigerant CHV is coming with?
Yeah, I haven't seen the final details on that, but yeah, I mean, I would agree with what you said. It's CO2 it's designed for high lift on the refrigerant side, high operating pressure ratio. Again, really meant to run at full maximum demand output. So you're not really doing a lot of modulation, even though these are inverter driven compressors. They're optimized for high lift. So you don't want over pressurization losses associated with low lift, low delta T. steady state type loads. And that's what you would have with this product if you tried to apply it in those scenarios. So it's again, it's really meant for that high operating system pressure ratio, high lift. It's optimized for that. So yeah, you'll see more non-transcritical type cycle, refrigerants being used in, heat pump water heaters for heating hot water, steady state applications.
Mm-hmm. Well, and so obviously, the as you pointed out, the EPA is mandating the removal of R410A as of, I believe, the end of 2024. Clearly, this system goes far beyond that. So you're meeting a standard that I assume hasn't even been laid out yet. I mean, has there been any indication that water heating at some point will be mandated fully to CO2? Have you heard any discussion on that?
I haven't specifically, but I mean, I'm sure, when we get to 15, 20 years down the line, where even these A2L refrigerants, can't comply with these GWP requirements, that we'll all be transitioning to things like that, whether it's propane or CO2 or obviously not ammonia, but at that point things may look very different. But that's pretty far down the line. So the next big transition will be to A2L. On the VRF side, with depending on the manufacturer, R32 or 454B typically is what you're going to see.
Yeah, mini split with the change by 2025, and VRF changes by 2026. So there's a little bit of time left.
Okay, but those aren't changes to CO2. Those are just sort of the next global warming potential down, right? Yeah. Cost, right? I mean, and that's the question. And if people are looking at these systems, they're comparing the costs of your standard, right, methane fossil gas powered boiler versus maybe a traditional R410A, which they can still use, at least for now, or even another refrigerant, versus, perhaps ground source heat pump, right? So what kind of cost comparisons, and you can put that in the context of, Inflation Reduction Act incentives, obviously, those incentives are different. I know on the ground source heat pump side, you're talking maybe upwards of 40% tax credit back for nonprofits. So how does this kind of play into that whole cost and incentive world as far as comparing it to your other choices out there?
Yeah, Mike, you probably have more data on cost. Some of this is variable, highly variable, depending on how these are being applied, whether it's piecemeal applications with all these components we talked about, or a skid application. That's certainly more costly up front. What you have space for with regard to storage versus recovery or heat pump output, number of heat pumps. So there's a lot of factors involved. I would say, you're probably in the 3 to 5 times range what a conventional system costs up front in many cases. But, where this is really geared towards are these electrification markets, where you're forced to move natural gas away from the end user. The utilities are going to start taking over, really the use of natural gas for peaking plants in combination with more renewables to clean up the grid. And where that's not available and your only options is electric or go to heat pump technology, that's really where the savings comes into play. And so it's not uncommon to see, 50% reduction in operating cost in those scenarios against an all electric solution. With gas, it's going, from an upfront cost standpoint and an operating cost standpoint, it's going to be hard to beat out gas in most markets, just because of the low cost of gas, per therm, per BTU, the dollar per BTU that you spend on that. Emissions aside, which would be higher in many cases with gas still. It's just economically that's not really where the product's driven. It's really meant for these electrification markets. So you may have 4 or 5 times the upfront cost, but you have 50% reduction on operating costs. So it's a fairly quick payback. But I don't know, Mike, you may have other data you want to share on that.
I'd completely agree. I think also some of that determines where you're located. If you're in Minnesota, similar building might require 2 QHVs versus if you're in Texas, you might have 1. So it's very specific. So if people are looking out, feel free to get in touch with us and at least let us know your market, because with heat pumps, we have to size on the ambient conditions. So that definitely fluctuates.
So I'm thinking in the context of cost and the conversation I always have with, property owners is, anytime we talk about any new system, they have concern about number one, maintenance, ongoing maintenance, and number two, are parts even available if necessary. What can you speak to on costs and, ongoing maintenance, especially as it relates to traditional systems?
Yeah, so the maintenance is not going to be any more than like traditional systems outside of you're going to have a condensing unit that you have to go clean the cottonwood off and make sure that that's good and do some little maintenance around that. So there will be more maintenance in terms of your boiler doesn't exist outside. It's outside. You got to take care of it. But parts, we have stocking programs for our parts that keep everything in stock for a number of years, even post production. Matt, I don't know if you know how long post production they go, but parts will not be a concern.
Yeah, there's plenty of planning for that for the foreseeable future with most manufacturers, I would say, just like with any other VRF product. Yeah.
And so are there, for these types of products, do the MEP contractors have to go through training and certification to install these, or is that an optional? Is the training just a sales training, or are there actual technical trainings?
There are technical trainings for this. We recommend everyone go to the training. Like, for example, all of our VRF products, there's training to get the extended warranty.
Oh, okay.
So you go from a 1-year part, 7-year compressor to 10-year part, 10-year compressor. The problem we see is not every contractor actually goes to training. No idea why. It doesn't matter. The engineer asks for it, the owner asks for it. Sometimes they just don't go. But yes, we do have training for this product. Highly recommended that people go to training, and I think we probably even force it on the new installations because it is such a new product right now. But if it goes the way the VRF goes, we'll see some people that don't do it, and then that's kind of unfortunate.
Well, and as you mentioned, you said you get extended warranty. So does that extend to this opportunity as well? You get that longer warranty as something a contractor can offer when they're trained?
Matt, do you know the warranty? I don't know it offhand, Brett, and apologies.
Yeah, I don't believe for the QHV currently that's extended to the same terms as conventional VRF. It is a little bit different just because of the complexity and water quality. There's a lot of variations here that are, outside of the control of even proper install and design. So I think it's challenging to offer that same type of extension. I don't want to quote it because I don't have that off the top of my head. I know they're looking at maybe changing some of that, but it won't be at the level of standard, VRF. With that 1010, I think it'll be reduced from that again because of some of those risks with water quality, and that's so location dependent.
How long until we're going to start seeing smaller CO2 heat pump water heater systems for residential use or small commercial use? Is that something that's coming?
There is a residential version coming. Matt, I don't know any of the timing. I assume we'll have some information in 24 because it does exist in Europe right now. Matt, I don't know if you've heard of timing on that.
No, yeah. I mean, neither Mike or myself are in the product management group. So that's out of our headquarters. And, I typically, even if we have information, we're leery to even quote some of that because it's always shifts and in flux. Once they start
and I just mean in general, like the market in general, what are you seeing and hearing? I mean, I know currently a lot of the heat pump water heaters are self-contained, right? Though I've heard of CO2 water heaters that have an outdoor extender, an outdoor condenser. Is it possible to get an indoor water heater where it's all self-contained with the CO2 inside, or does it have to have that outdoor condenser? You know what I'm saying?
Yeah, I don't have much information with regard to what exists out there that's CO2 based for residential.
I wish I had additional
information on that. I'm sorry.
No, that's okay. I mean, I think it just speaks to how there really isn't much. I mean, I think that's really the answer.
Well, it is a big untapped market. I mean, like Mike mentioned, we've attacked aggressively, throughout the world and more so here in the US in the last 10, 15 years, the heat pump heating side of buildings on the HVAC side. But this is really the frontier of domestic hot water.
Right.
We're just starting.
So negative 35, I mean, obviously the idea that we even get to that is so rare, especially these days as it's just getting hotter and hotter. You know, but if, on the flip side, of course, we have extreme cold snaps, but that low, I don't know. But in the event that that happens, is that backup electric resistance swing tank kind of your fallback? I mean, that's usually the case with traditional air source heat pumps. You know, I know a lot of the market residential water heaters have the backup resistance built in case you run out of hot water. Is that your backup, or are you really just out of luck at that point?
Yeah, for extreme climates like that, you really need to consider other means,
Yeah.
because even with those swing tanks are really optimized for the maintenance loads, and to really cover, an extreme scenario like that in that type of
Mm,
climate, those are much smaller storage volumes. So it's, again,
mhm,
that whole, going back to the whole sizing profile and how you handle that profile under a peak design day, um,
mm,
relies on the heat pump sizing and the storage
mm,
volume. So you have to
mhm,
start with sufficient capacitance and then have enough heat output to maintain that capacitance, capacitance being your storage temperature. Um,
mhm.
and so the swing tanks typically aren't sized for that. You just don't have space for it. So at that point, you would have to, if you're under those type of extreme environments, you would have to have some other redundant system in parallel with its own pump,
Yeah,
that came on and circulated that big primary storage tank volume to
right,
maintain that capacitance and maintain that profile, that low profile,
right.
until those came back on. So
Yeah.
yeah, that's a really good question, because that is certainly important when you get into North Dakota, Minnesota, Upper Minnesota, things of that nature.
Yeah, Canada, I imagine,
Yeah.
any of our Canadian friends. Um, so some of these different modeling tools you mentioned, I'm curious, I'd imagine with a product that is CO2 based, you're getting that embodied carbon reduction benefit because of the high global warming potential of all the other refrigerant opportunities. Is that showing up in any of these modeling softwares where, again, I know a lot of the modeling you talked about was mostly to model it to make sure you have enough um, hot water, right? I mean, that's the number one concern. But I know also these modeling systems are looking at your energy efficiency, your savings. ASHRAE 90.1, 179D tax credit could be worth $5 a square foot, right, through Inflation Reduction Act money. But you know, I'd assume there trade-offs in energy efficiency if you were to use a higher global warming potential refrigerant, but maybe the modeling would also show that embodied carbon, right? And so it's showing you, hey, overall, your carbon is reduced because you're using CO2, even if the operational side is a little higher. So, long story short, are you seeing any of these modeling softwares also sort of look at that version of carbon, or is it just really the operational carbon?
Yeah, so far I'd say it's primarily looking at operational carbon from,
Mm,
energy consumption, resulting energy consumption, not total life cycle, you
right.
know, carbon impact, based on the life cycle and leakage rates of the refrigerant. Some of that data is hard to ascertain and quantify accurately.
Right.
And that's been always kind of the challenge with that, is leakage rates. And, certainly people could be biased with
Mm,
that to skew the results. Um, so yeah, that right, as of what I've seen, currently in the past leading up to this launch, it is primarily just looking at operating cost impacts, operating energy impacts in terms of CO2.
yeah, that
Hey,
makes
Matt,
sense.
one question that came up. I know we can operate down to negative 35. You know what the high end limit is? Is it 126 like
Um,
VRF, or is it
It's above 100. I think it's close to 113 or more. I'd have to pull up these data charts, but yeah, I think it's
okay?
somewhere around 104. Now that's just the tested limit. I mean, the limit of test data. Um, it'll operate much higher above that, um, before it probably goes off on high discharge temp. There probably,
Okay.
just like with any VRF, there'll be some upper limits of high discharge temp protection. on those compressors. So I would have to look that up out of our service manual. I don't have that off the top of my head, but you probably got, at least a 10-degree buffer, if not maybe more, between the charted maximum, which again is probably close to, I think it's close to 104, slightly above, before you actually get into discharge temp protection.
Yeah, help me understand that, because your goal is to take water and get it up to what, 120 degrees, whatever. Why would there ever be a maximum? Is that just because the system can't handle it, could damage it, or?
Well, we're just talking about outdoor
Outside air
conditions.
Right. And wouldn't it be in your favor when you're trying to heat water to have the hottest air outside? I mean, that seems to
Well,
be.
yeah, it certainly is up to a point, but because of the heat of compression and superheat and what that does to discharge
Okay.
temperature on the compressors, there'll be discharge temperature pressure limits
Yep.
because you're operating between those two, heat sink reservoirs. And so when that low side climbs up, that evaporating side climbs up significantly above the upper range of our test data. Again, typically 10 degrees or more
Okay.
above our peak ambient tested data. Then you start getting into potential discharge temp protection issues because of superheat on the compressor, just because heat of compression.
I got it. That makes more sense.
Yeah.
And as far as modeling out having enough demand for the flow rates, what conversation comes into play, especially in the modeling, with low flow rates, water sense certified fixtures, Energy Star certified dishwashers and clothes washers to reduce energy, or even training on water efficiency management, especially in commercial operations? I assume people can be trained to be more efficient. How does that come into play within the modeling side?
Yes, yeah, it's a really great question. So typically that process, with the typical Division 22 plumbing design process in the consulting world, it's whether it's heat pump water heaters or conventional water heaters, it's going to be very similar up until that point. So you're evaluating the types of fixtures you're going to use or want to use and specifying the project. You're looking at their flow rates and you're assessing and determining a peak total building gallon per hour rate. What's the maximum?
Mm-hmm.
And so once you have that value, whatever that's based on, and the selection of fixtures and devices and in that facility, that's the value that you really need to start working with and apply to a building profile.
Mm-hmm.
And extrapolate that to a usage profile, because obviously you're not going to have that peak every hour of the day. That needs to get applied to a representative building profile. And like I said, in most cases, designers just don't have a good feel for what that should be. They're not used to sizing things that way. They take that value that they come up with, that peak gallon per hour rate, and they apply conventional, storage and demand factors to it, and that's how they size the water heaters, because that's always worked and it's been safe, and they've never run out of hot water when they apply those conventional methods. But with this technology, you're typically significantly oversized, you run into issues with higher upfront cost, minimized runtime, excess cycling. And so we're typically going to have much larger storage volumes, 1.5 to 2 times what you normally end up with smaller heating output plant capacity. So we've got to have that profile, that 24-hour profile. And that's where they're taking that peak gallon per hour rate and extrapolating it, typically to an ASHRAE profile, whether it's the max daily use or max hourly use profile that we kind of showed. It's typically what designers have to go with. Now, again, for multifamily, I think in most cases we would defer folks to just use the built-in functionality in that EcoTope tool, because they've got a lot of good empirical data that they've gathered from metering multifamily buildings. It's kind of their niche. And so they've refined, that sizing methodology based on the data they've collected for multifamily use.
Okay, yeah. So you're going off of the assumptions, but does that tool, is it designed for low efficiency inputs assumptions?
Well, yeah, efficiency, the heat pump
Or
water
high
heater.
efficiency?
Yeah, it doesn't really
Oh,
factor into that, because the goal of that sizing method in that procedure is to generate that sizing curve, which is a trade-off curve between storage and heat pump output. And that could be anybody's heat pump. We're not looking at derated capacity or efficiency at that point. You're looking
Yeah.
at what's the minimum output you need for this specific storage that you want to target. And so once you have that data, then you can start looking at manufacturer data and applying that requirement to see what makes sense in terms of number of heat pumps, and then it start analyzing efficiency from there.
Yeah, and what I meant, I'm sorry, the water efficiency. So if you're, their tool is saying, oh, your assumption is a baseline versus a more water efficient building. I mean, does it allow for that kind of thought?
Yes, yeah, absolutely. Yeah. There's some defaults in there to pick from for multifamily, and then they have recommendations obviously based on the data they've collected. But yeah, you have full adjustability over that. And again, if you disagree with any of those inputs for the multifamily assumptions and you want to use a completely custom input, you can. They have that capability as well, so you can enter this data hourly.
Right.
And then again, at that point, you're taking your building design peak gallon per hour rate and you're extrapolating it to the profile you want to use, and you can enter that into the tool as an alternate method. In a lot of cases, people may do both and then compare the two. And at the end of the day, there's got to be a comfort level with the designer to pick, to make the selection of what they think is reasonable for their building. But yeah.
Yeah, and there was a good question in here. So Mike, I don't know if you want to expound upon it, but trying to figure out where that cutoff ratio is of how many units you have in a building before you want to probably go to a more individualized heat pump water heater versus a central system, which I assume is the conversation you're having here. And is that cutoff different with CO2 water heat? So let me use an example. Does a CO2 central water heater system say you should probably have this many units versus a traditional central water heater says you should have this many units? And a 20 unit building, do individual units. I mean, what are your thoughts on that?
Yeah, so because of the size of these units, there's a low limit on them. So it depends on if we're talking about a 28 building condo here. If it's all a bunch of three bedroom units with a lot of showers, that's going to be probably more applicable versus I think one project we looked at was 40 units and they were more on the studio level. That was a little too small. So it kind of depends. I'd say 40 to 50 units is really the minimum. But if you have a lot of 3 bedrooms and something like that, then maybe we can drop a little bit lower than that. And it's just really dependent on how CO2 refrigerant works. The equipment's designed to run for 12 plus hours a day. And if you get into some of these smaller units where it might run less than 12 hours, and Matt can probably expand on this, it's not ideal for the equipment and it's probably not the right application.
Yeah.
Oh, okay. So
yeah,
you're
that's
saying
kind of what you end up with. You analyze those situations, and again, you develop that sizing curve.
Right.
And if you can't really get a reasonable selection, with the minimum output capacity that we offer under those design conditions and achieve, again, at least 9 or 10 hours of runtime a day, then that's probably a bad application.
And that runtime is how many gallons per minute again?
It's not really gallons per minute. It's just the runtime for the heat pump. So and it's kind of hard to explain this without looking at maybe an example, but out of that tool, whether you do this manually or you do this, with the EcoTope tool, the end result is you get a sizing curve. And that curve is just a trade-off between minimum heat pump output and storage. And so, if you're anywhere on that curve and you're ending up with, run times that are well below 9-10 hours a day. So you may have such a small system that even if you reduce the storage volume significantly to the very tail end of that curve, so the lower storage volume, the highest heat output, and even at that condition, you're still below 9 hours, 10 hours a day of operation. That's a bad it's a bad application.
What happens when you fall that low? What are the ramifications?
It's just potential for excessive cycling. So again, these are optimized for high lift and to run multiple hours a day at basically peak load demand to recharge these tanks and maintain, that storage capacitance. So, they have a limit in terms of number of start-stop cycles. So again, they're not meant for low loads, steady state modulation for long hours. They're meant to operate, again, at least 9-10 hours a day at full capacity demand because they're high lift devices, right? So
I see.
they don't want to cycle on and all. I mean, it takes, there's fatigue and wear and tear by cycling these excessively to meet a small steady state load. So they need something to chew on, if you will, and they have to keep them running, at least 9 or 10 hours a day typically. So
Okay.
it's just the nature, it's a limitation of the profile because of the building size. It doesn't matter how small you make the storage, you just can't get enough runtime hours where it's a
Right.
feasible application.
So a traditional living situation in the normal world, I guess, not where we're all locked down maybe, but people come home, they use excessive amounts of water, cooking, shower, cleaning, they go to sleep, they're not using the water, they wake up, they do the same thing, then they're gone all day. That sounds like it's not applicable then, right?
Well, on a really small scale, it may not be. Yeah. When
Okay,
you
but
start dealing with
if you're
diversity and multifamily with a lot of diversity and different, it really depends on the size of the building and that, that sizing curve.
Right. Interesting. Well, I know you were explaining that earlier, and I think just the way the question got asked, it sort of.
Yeah, it's hard to explain without walking through like an example.
Yeah.
We can certainly do. If people have questions, just get with us and we can walk through that with you on the actual application.
Yeah. So on that note, we are at our time here. And Mike, I don't know if you want to reshare your outro slide there with some contact information.
Sure.
But I would ask, where can people go to learn more about this technology, reach out if they have any questions?
Yeah, so you can definitely reach out to myself, and even if you're in a different market, I can certainly relay you to your proper person. I cover the state of Michigan, but we have associates all over the United States. We have our website, train.mylinkdrive.com. That's for all of our traditional equipment. And then the Heat2O website is actually going to be the promotional website for heat pump domestic hot water heaters. But in general, you can definitely reach out to me and I can put you in the right direction. If you are in, the 13 states that Matt and I cover, Matt would definitely be involved with it. And if you're in another state, then we can direct you to the right person without a problem.
Great. Well, Matt, Mike, really appreciate your time. Appreciate Mitsubishi having you all out and all the work you all are doing. I learned a lot. Thanks for educating us, and take care, everyone. We'll catch you on our next session next week. So thank you so much.
Yeah. Thank you, everyone. Really appreciate the time.
All right. Thank you.
Bye.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.